So here we go. We're going to solve it. Now, I just try to clean this up a little bit. The previous slide, we had all of this work, and now I'm just going to attack it on this one. Okay. So here we go. I need to take the derivative. So dd dt, which would be here, let's see, the partial of d with respect to x. Hopefully you're pretty good at square root functions, as that's what that derivative would be with in terms of x, times the derivative of x with t, which would be just 4 sine t, don't forget the negative there, plus partial of y, again, 2 square roots x squared plus y squared, all over, or with 2y on top. And this guy's derivative would be 2 cosine t. Now, let's go plug in. Okay. Now, again, I mentioned this before. There's an issue here. Everything is in terms of x's and y's and t's, but I'm only wanting dd dt. But we can kind of look at some of this stuff and realize, let's kind of build a bank over here of some information. Here's my bank of information where t equals pi. If you remember from our little orbit that we had, this was 1, 2, 3, 4. Okay. So right now, at that moment, x equals, I'll put it in my bank, sorry, x equals -4, y equals 0. If you want, you could get that straight from this part. Okay. So x is -4, y is 0, and my time is pi. So with this kind of bank, I can plug all that stuff right into here. Okay. So if I want it, I go dd dt when t equals pi. I have, well, the 2's cancel here, so I got -4 over the square root of 4 squared plus 0 squared times -4 sine of pi. Sine of pi is 0, so all that goes to 0. Plus, let's see here, if I plug in y, I get 0 all over square root of 4 squared plus 0 squared times 2 cosine of t. Let's see, 2 cosine of pi is -2. Well, in all of this, this one happened to miraculously be, my rate of change is 0. Now, at first glance, you might go, wow, that was really lame or really boring. What does that mean? How does it become 0? Well, let me explain it to you visually with the orbiting. So, if you remember, 1, 2, 3, 4, or 1, 2, 3, 4, 1, 2, 1, 2. Here is my track. And as I have my guy going around it, let me ask you, from here to here, is my distance getting bigger or smaller? From this distance to this distance to this distance to this distance, the whole time that distance was increasing. But later, once the red guy gets over here, my distance starts to decrease. So this dt would be negative, and this dt would be positive. Well, if it goes from positive to negative, at some point it has to be 0. That point right there is the balancing point between turning from green to blue. So I'm getting bigger, 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 bigger. Right at the black point, I start to get smaller, smaller, smaller. So that means right at dd dt, right at that point, it had to be 0. Okay? So that was one of them. Let's take a look at a bigger chain, because we've done a couple examples now of the same looking chain. Let's upgrade it. Here comes the upgrade. Okay? I'm going to do the same idea. If you notice, this guy is the same track. So let's draw this to kind of see what in the world is going on here. So this guy is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 1, 2. So this guy's moving just like we've had before. That way. Now this guy is a totally different object, which he's moving with 2 sine 2t, 3 cosine 2t. So my x's bounce between 2 and negative 2, and my y's go up to 3 and negative 3. So it's going like that. Okay, and I'll show you there's one guy here, and there's one guy somewhere on the other, and I care about how this distance is changing between those two guys. Okay, so let's see if we can use the distance formula again. Distance equals x2 minus x1 squared plus y2 minus y1 squared. Now notice, all of these guys are variables now. Just unlike the last one where this x1 and y1 were just the origin, now I have the red dot and the green dot, and they're always changing. So if I want to look at this chain rule, it would be this. I would have a d. He varies with x1. He varies with y1. He varies with x2. He varies with y2. All 4 of those guys are changing. So each one of these varies in terms of a t, varies in terms of a t, varies in terms of a t, varies in terms of a t. I just upgraded my chain rule. Okay, and like I said, if you can draw the picture of the chain rule, you're going to be fine. All of these black portions of the chain rule are all partials. And all of the blue are full derivatives because they're directly tied only to one component. So if I wanted to show the chain rule here, I know this just got a little bit smaller, sorry about that. I would be saying this, dd dt equals, and it's a huge formula full of partials. So it could be the partial of d in terms of the partial of x1 times dx1 over dt plus the partial of d with respect to x2 times his full derivative, dx2 over dt, plus the partial of d in terms of the partial of x3 times his whole derivative, and plus again the partial of d over the partial of, oh, when I said x3, I'm sorry, I just started getting in a groove. Instead of those, I should say d partial of y1, that's my fault, dy1 over dt, and it would be the partial of d over the partial of y2 with his full derivative. I know this is a lot bigger, but this is the Calc 3 component of it, is making sure you're okay with how this was upgraded. And notice I did the x1, x2, and then the y1, y2. It doesn't matter the order when you're adding. So if I wanted, I could solve this problem. Okay, if you take a look at it, you definitely know all of the blue derivatives because they're all very simple with the 4 cosine t, the 2 sine t, the 2 sine 2t, and the 3 cosine 2t. Those are easy derivatives. And the only thing you might be wondering about is how in the world do you take the partial derivatives with respect to each independent little guy. So let's just take a look at that. I'm going to copy this guy. I'll just show you how to set up that partial. I'm going to copy him, put on the next slide here, and let me paste it in. Okay, just to let you know how to do the partials, if I wanted to do, let's say, the partial of d in terms of x2, let's do x2. Well, that means this is my variable, and he's a constant, he's a constant, he's a constant. It's just a normal square root derivative. So that means I would say 2, and all of this stuff goes in the bottom. And then on top would be the derivative of the inside. Well, the derivative of the inside here is really only coming from this piece, because that's the only part that has the variable in it. And I would say that piece's derivative is 2 x2 minus x1. And the derivative of the inside of that, the derivative of x2, is just a little 1 there. So that's what that partial would be. And it would be similar for all of the partials. And you can piece together the whole formula for the chain rule, and you can get your answer. Now, for you guys, because you kind of have 2 days to dissect and engage in the chain rule, you might want to take a look at page 877 and look at example 2 and follow it through. This is example 2 on page 877, and it shows you how I can solve it all the way down to get your final answer. Okay, I'm not going to do this for the notes, but I want you to take a look at it now before we resume with the next video.